On our final day of Physics 30, we're going to spend some time talking about a guaranteed numerical response scenario that we're going to see. I told you guys yesterday that you're going to see a graphing question. You might see more than one question involving a graph, but you're going to see one question that's dedicated to graphing. And you know what to do with that, right? You take your numbers, you put them in your calculator, you get the slope, you get the y-intercept, and then you find out what the slope means, find out what the y-intercept means, and then you figure out what you need to figure out. But there's another set of numeric response questions that are guaranteed as well. They're called the physics principle questions. Years ago, we used to have written response questions on the diploma exam. Written response questions were each worth 15%, and they were hard, and you had to show your work. That was a good thing because it allowed you to show process. And a multiple choice question, if it's wrong, it's wrong. But a written response question, if you knew what you were doing, you could still get a 3 out of 5 or a 12 out of 15 or a 9 out of 15 or a whatever out of 15, right? You could still get some marks by showing process. Since they've gotten away from the written response questions, they've tried to create numeric response questions that kind of get you to show process. And those are those physics principle questions that we're going to talk about today. You will get at least 2 of these questions. They guarantee us that we're going to get one group of 2 questions involving these physics principles. Lately, they've been putting a little bit more on there than just the group of 2 questions. So if you happen to see 4 or 5 that talk about physics principles, that's okay. It ends up being the same thing, but we're guaranteed of seeing a group of 2 of them. And in all likelihood, to be honest, it's going to be the last 2 questions on the test. That's what it's been over the last couple of years, always appearing as the last 2 questions on the test. So here's what it's going to look like, basically. Thank you. You're going to get a question that asks you to solve for something. And now what they ask you to solve for, I have no idea. Okay? You'll find out before I do. You'll find out the day of your diploma exam. You're going to solve for whatever they're asking you to solve for, just like you would any other numeric response or multiple choice question. Solve for what they ask you to solve for. But the follow-up question is going to ask you basically, how did you do it? What physics principles did you use in order to solve it? There's a list of 9 physics principles on your data sheet. Bottom left-hand corner of your data sheet. I'd like you to look at that data sheet right now. The handout that I gave you has those principles on it, but I want you to know where to find it on your data sheet. Look at the bottom left-hand corner. You're going to see a list of principles that looks exactly like this list on the board here right now. We're going to go through each of these principles just to make sure you know what they're talking about. As long as you know what they're talking about with each of these principles, and it's not that hard, then you should have no problem attacking any question they throw at you. We don't need to do more material to be able to answer this question. We don't really even need to go over this because you know this already. We just need to make sure you know what they mean by each of these principles. Principle 0 says uniform motion. And by uniform motion, we mean things that are going at a constant velocity. So basically, if in any part of the question you used v equals d over t, then you used principle 0, and you'll list that as one of the principles that you use. So if you use v equals d over t, then write down principle 0 on one of those questions where they ask you to identify the physics principles. Topic number 1, or principle number 1, is accelerated motion. So whenever you have an object that's speeding up or slowing down, you've used principle number 1. That could include using F is equal to m times A is equal to delta V over delta T, and so on. All of those different acceleration equations that you learned about back in Physics 20. D is equal to VIT plus 1/2 AT squared, and so on. If it involves speeding up or slowing down, then it involves principle 0, accelerated motion. Now, be careful here. Topic number 2 is uniform circular motion. That means when an object is moving in a circle, right? And that's pretty self-explanatory. But when an object moves in a circle, it involves an acceleration. Okay, it's accelerated motion. It's an acceleration toward the center of the circle. What you want to be careful of is that you don't list principle 1 and 2 together. They won't take that. Okay, so if you have circular motion, you do have accelerated motion, but you can't say principle 1 and 2 together. If it's going in the circle, go with principle 2, even though it is accelerated motion technically. Okay, I call them redundant principles. Okay, one kind of takes over the previous one. Okay, if it's going in a circle, even though it's accelerated motion, we're going to call it uniform circular motion. Basically, if you use the equation mv squared over r, then you've got a uniform circular motion. And I'm trying to think of situations where you use that. Lots of times in physics 20, but in physics 30, for the most part, uniform circular motion, I think, would probably appear when you've got a charged particle moving in a circle in a magnetic field, right? And you set Fc equal to Fm. That would be a principle 2 problem, uniform circular motion. Work energy theorem, it just says W is equal to delta E. That's work, basically the definition of work. Work is equal to the change in energy. I'll be honest with you. The work energy theorem is not something that I would use normally to solve one of the problems in these physics principle problems, because generally we can use conservation of energy to solve those problems. And that's my preference, is to use conservation of energy. So we're going to write that down. And if you do happen to use that, that's great, list principle 3. But odds are, if we're solving a problem involving energy, it's going to be principle 5, conservation of energy, as opposed to principle 3. Principle 4, conservation of momentum, I think that's pretty self-explanatory. If you got a collision explosion, if you use Pi equals Pf, 1 dimension or 2 dimensions, then you've got conservation of momentum. Conservation of energy, Ei equals Ef. And in physics 30, that usually manifests itself in a question where your charged particle is speeding up or slowing down, right? QV equals 1 FmV squared, or vice versa. Now we're getting into some more recent stuff here now. Conservation of mass energy. What's that one? What equation would I use with conservation of mass energy? Equals mc squared, right? If I used equals mc squared, then I've used conservation of mass energy. Conservation of charge. Well, there's lots of places that could appear, right? And back in Unit 2, in our electricity unit, when we touch two things together and the charge is balanced, that was conservation of charge. When a neutron decayed into a proton and an electron, that was conservation of charge, to make sure that we had that electron emitted as well. But honestly, most times you see conservation of charge or conservation of nucleons. Most times it appears in a nuclear equation. Not always, but most times. Something like this. You got uranium-235 going to an alpha particle plus thorium-231. If we're balancing these numbers, then that would be conservation of charge. If we're balancing these numbers, then that would be conservation of nucleons. Now, again, it's not to suggest that you can't see conservation of charge somewhere else, but that's probably the most common place that you'd see that, right, Leah? And then wave-particle duality. Generally here we're talking about HF, or hc over lambda, the energy of a photon, right? Relates the wavelength to the particle nature of the photon. The momentum of a photon is h over lambda. The energy of a photon is P times C. Those equations that appear later on in the year, basically. Basically, equations that we learned after the photoelectric effect. Post-photoelectric effect are pretty much wave-particle duality here. Now what I want to do is take a look at a question here. There's 3 questions in the booklet that I've given you that are examples of this type of question. I'll be honest with you, all 3 of those questions are probably harder than average. The one that you see on your exam, no guarantees here, but will likely be easier than the 3 questions that appear in that booklet, at least easier than the last 2. The first one, the one that we're going to do, is probably a little bit harder than average, but is certainly probably closer to what you would see than the last 2. The last two are older questions, and they used to make these ones harder than they do now. At least that's the pattern that I've noticed over the last few years. They've gotten a little bit easier. I've given you those hard ones because, listen, if you want to work on something, if you want to practice on something, practice something that's hard. And then the ones that are a little bit easier seem even easier at that point. We're going to do the first one. The first one that appears under scenario number 1, and it talks about a cyclotron. I'm going to give you probably about 5 minutes to take a look at that yourself and see if you can identify, not solve the whole thing yourself, because you're not going to solve this whole question in 5 minutes, but if you can identify anything, identify a principle or figure out something that you're going to do. As you're reading through it, make notes. If something jumps out at you as being maybe something that might be useful later on, make a note of that. And then we'll go back with that information when everybody's finished and take a look at it and solve the question. Okay, 5 minutes starting now. Let's have a look now then. This question talks about a cyclotron. We've actually talked a little bit about a cyclotron, but that doesn't really matter. That's not a curriculum objective. We don't have to talk about a cyclotron. We just did because we talk about certain examples that we may or may not see on a diploma exam. If we happen to open up our diploma exam and see an example that we've talked about, then we got lucky. Okay, there's a good chance that maybe one of the examples will be on there, but there's a good chance that none of the examples that we've talked about will be on there. We don't need to worry about that. Okay, even if it's not examples that we've done, they explain it. Right? They talk about a cyclotron, what it is here, and how it works. It says a cyclotron is a type of particle accelerator that can be used to accelerate charged particles to very high energies. And we know why that is, right? We know that they've got to be high energies so that when they collide, we can overcome those nuclear forces and cause these things to break apart and see what's inside. A cyclotron consists of two hollow metal electrodes that are each shaped like the letter D. And you can see that picture down here, right? Each shaped by like the letter D here. It says the Ds are placed in a vacuum and an external magnetic field is added. Charged particles are injected into the center of the Ds. An electric potential difference across the D separation accelerates the charged particles. This is the first thing that I really noticed as being important here. Okay? An electric potential difference accelerates the charged particles. What do we do when a charged particle is accelerated? Think back to topic number whatever it was in your Physics 30 and 16-page booklet. There's something that we always do when a charged particle speeds up or slows down. What is it? Somebody's got a little bit more reviewing to do, I guess. EI equals EF. Right? It's like a car going down a hill. Car speeds up as it goes down the hill. We have a conversion of potential to kinetic. Charged particle speeds up as it goes across the potential difference. We have a conversion of potential to kinetic. It's just electric potential, not gravitational potential. All right, I don't know if I'm going to use that or not, but I noticed a charged particle was speeding up. I know that this is something that I may use, so I'm going to draw attention to it so I don't forget it. Okay, if you're anything like me, you read through this, you don't make a note of it, you get to the end of the question, I forget all about that little thing that I noticed early on in the question that says EI equals EF. All right, it says once inside the Ds, the charged particles follow a circular path. Wait, I remember a minute ago it talked about a magnetic field. A magnetic field, circular path. That's the second thing that I notice here. When we have a charged particle in a magnetic field going in a circle, we usually do this, right? FC is equal to FM. MV squared over R equals QVB. Again, we don't know if we're going to use this or not, but we know that it's something that we can use if we have enough data and if it's useful. As they reach the D separation, the electric potential difference reverses so that the particles are again accelerated. This continues each time the charged particles travel faster and faster and faster. One particular cyclotron is shown below, and then it gives me a bunch of data. I don't really care about the data. I mean, that's going to be important, obviously. But what's important to me right now is that I identified what's going on in this question, not what are my numbers. Remember, we've said right from the beginning of the year, it's not so much the givens that are important, it's what's going on. Like, what's really going on here, as opposed to the actual numbers that we have given to us. All right. what does the question say? That's a whole page of information to get to the question. Number 13 says the radius of curvature, the path of the proton in D immediately after it's crossed the D separation. Immediately after. Okay, we're given a speed before as it approaches the D separation, not after. So that's not the speed we want there. Okay, we'll worry about that later on though. Okay, we know that when it goes in a circular path, we know that we can say FC is equal to FM. Okay, we already identified that earlier on. I'm just going to use that now. MV squared over R is equal to QVB. I'm going to cancel one of the V's. I'm going to rearrange that to solve for, what were we looking for? R, I think. The radius of curvature, looking for R. Rearrange this to solve for R. The R goes up by multiplying. The QB goes down by dividing. And it looks like this. We're talking about a proton. We know the mass of the proton, 1.67 times 10 to the minus 27 times, we don't know the speed, okay? Because the speed given to us is the speed as it approaches the gap, not after it goes through the gap. The charge of the proton is 1.6 times 10 to the minus 19 times the magnetic field strength of 0.863. Okay, so we need the speed. We don't have it yet, but we identified something as we were reading through, something else that's applicable here. The whole conservation of energy thing as it accelerates across the separation. When it speeds up, it must start off with potential energy. But in this case, it also starts off with kinetic energy because it says the speed as it approaches the separation is this value. We need to know the speed that it leaves the separation with, the final speed. So it's like a car going down the hill that's already moving at the top of the hill. It's got potential energy and kinetic energy, but at the bottom of the hill, it's got just kinetic energy. Let's sub in some numbers here. The proton is 1.6 times 10 to the minus 19 coulombs. The potential difference here is 0.2 times 10 to the 6 volts, 0.2 megavolts, plus 1/2 of 1.67 times 10 to the minus 27, the mass of the proton, times VI squared equals 1/2 of the mass again, times VF squared. Let's get VF. That would be the speed that it's moving after the separation. Let's say 1.6 times 10 to the minus 19 times 0.2 times 10 to the 6. We get 3.2 times 10 to the minus 14. That's the first term right here. Now, let's add that to the second term, which use some brackets here, 0.5 times 1.67 times 10 to the negative 27 times 2.5 times 10 to the 6. Now, unless you're going to use another set of brackets, make sure you use the EE button right there. Okay, the EE button for times 10 to the 6. Because if you say 2.5 times 10 to the exponent 6 and then squared, you're going to square just the exponent, not the base as well. We want to square the 2.5 as well, the 2.5 times 10 to the 6. So use the EE button to do that, or insert another set of brackets in there. Do that. Now we've got the whole left-hand side. Now let's subtract from that brackets 0.5 times 1 point. No, we're not going to subtract, are we? We're going to divide that, aren't we? Let's divide it by 0.5 times 1.67 times 10 to the minus 27. And then we square root that. And we get 6.676 times 10 to the 6. That's how fast the particle is moving after the gap, after the d separation. Let's take that number, plug it into here, and we get the radius. So we'll take that number, we'll multiply it by the mass. Let's divide it by, use some brackets here, 1.6 times 10 to the minus 19 times 0.863, end the brackets. I get 0.0807, 8.17 times 10 to the negative 2. There's my radius, 8.17 times 10 to the minus 2, which is 8172. All right, let's do the follow-up to that now. It says the two physics principles, and this is really why I wanted to do this question here, not because of the first part. I mean, as much as it's a little bit tricky, okay, I think that you can figure out that first part. The second part of the question, that's what's a little bit new to us. Which physics principles did we use to solve this? Hey, you tell me. Take a look at your list right now on your data sheet or on that sheet that I handed out to you that has the physics principles 0 through 9 listed, and I want you to tell me one or both of the physics principles that you used. I don't care what order they're in, just tell me one or both of the principles you used. Good. We use conservation of energy, and conservation of energy is principle number 5. We use conservation of energy when we set EI equals EF. What's the other principle we used? Good, Christian. The other one is principle 2. Now, it tells us to list them in order. They tell us in Physics 30 information bulletins that come to teachers that it doesn't really matter what order we list them in. They'd accept 5225, but they always tell us on the exam, list them in order. So we're going to do that just to err on the side of caution. Okay. Now, what order did we do them in? Well, it kind of depends upon how you started, right? I started with principle 2, and then I went back to principle 5, and then went back to principle 2. So what do? Here's the rule. The one that got you the answer, which is principle 2, is the last one you list. Don't start with the first one. Don't worry about which one you use first. Worry about which one you use last. I used principle 2 last. I also used it first, but that doesn't really matter. I used principle 2 last, therefore we're going to list principle 5 as being the one that we used first. I don't see any other way of answering this question, but there are questions that involve 3 or 4 physics principles, and sometimes we have different options. Maybe you used 2 principles, you used 2 different principles. The answers will be key to accept any possibility. Okay, they've done these so many times and done so many different possibilities. Okay, if you think of a legitimate way to do it, they've thought of it. Don't worry if you come out of the exam saying, oh, I use principle 2 and 5 and I use principle whatever and whatever. If you both did it correct, you'll both be marked correct because you'll end up with the same answer, right? Just 2 different principles. Now, one final thing before I answer your question on that. If, just need to go, okay, go ahead. If you can't solve the question, you get like, you're doing this and you're underlining things and you're like, I just can't get it. Like I'm messing up. Every time I try going through this, I'm messing up. Guess what's going to happen? You're going to get that question wrong. But the follow-up question to it, you don't have to get that wrong. Question 14, even if you made 14 mistakes in the math, you can still nail question 14, right? Still nail the physics principles. Okay, so sometimes people don't like these questions, but I do. Because I think, really, if you can do the first question, like, how hard is it to get just to tell it what you did? Okay? And if you can't do the first question, well, then you still might be able to get the second one. You still might be able to tell it what you should have did. You just couldn't do it. Okay, this question, hopefully we get everybody gets 100 on both of these questions. But this question should be better marks than this question. Okay? Because everybody gets this one, that gets this one, should get this one. And even some people that don't get the first one should get the second question. All right? Guys feel comfortable with that?